Let's say we were given something like the derivative is equal to 2t minus 3. We were told a point on the original, that is f of 0 equals 5, and then asked to find a different point on the original, in this case f of 3. Now I want to show you one way to do it first that we probably have done before in this class, but then show you what can be a faster way. So first of all, we're told to we need to find the original. So we'll start by taking the antiderivative of this. We would get t squared minus 3t plus c. That would be the general solution. Then we can find the particular solution by solving for c using this point right here. We plug in 0 for t and set the whole equation equal to 5. So we get c equals 5. So now we have an equation, t squared minus 3t plus 5. So they ask us to find f of 3. We can do that by plugging 3 into that equation. Sorry, extra parenthesis there. And sorry. Let me just try that one again. Clearly something was going wrong with my brain on that. So 3 squared minus 3 times 3 plus 5, and that will actually turn out to be 5. Just a coincidence, that was the same thing that it was at 0. Don't pay attention to that. But you can see that this is one way. There's nothing wrong with the way I showed you. If you're given the derivative and one point on the original, you can find the particular solution by taking the antiderivative and plugging in that point to solve for c. And then if they ask you to find another point, then you can plug that value in to your particular solution. Nothing wrong with that, but there is a faster way, and I want to try to explain how it works. If you think about the example I just showed you, we had f prime, or I should put t there. We had f prime of t, and we knew one point. But we were asked to find a different point. So we were given a derivative, we were given what f of 0 equaled, and asked to find what f of 3 equaled. Well, there's a way we can relate these three things, and that's with the first fundamental theorem. Because if we took the integral from 0 to 3 of f prime of t, that would give us f of 3 minus f of 0. Because we would just take the antiderivative, which would be f, plug in the top number, 3, minus the bottom number, 0. So then go back to what we said. We actually know what f prime is, so we can do that. We actually know what f of 0 is, and we need to solve for f of 3. So another equation that we can use when it comes to the first fundamental theorem, we can get by adding f of 0 to both sides. So f of 0 plus the integral from 0 to 3 of f prime of t dt equals f of 3. So we can actually solve for a point on the original function using this formula. Or more generally, the way we do it is we say, first fundamental theorem says the integral from a to b of f prime of t dt would be equal to f of b minus f of a. So if we wanted to solve for f of b, we would just add f of a to both sides. So this is the same thing I wrote up above, it's just saying it more generally instead of using it specifically for that one example. So if we want to solve for an equation, a point on the original equation, we can do it using this formula. So let's try that with an example. But if you haven't already, please write this down. It's very important for what we're going to use. So they tell us that from 0 to 6, a particle is moving along the x-axis. The particle's position is not explicitly given, but the velocity of the particle is, it's that equation 2 sine of e to the t over 4 plus 1. The acceleration of the particle is given by a of t equals 1/2 e to the t over 4 cosine e to the t over 4, and x of 0 equals 2. So for what we're doing, we actually won't need this. If this was a multi-part problem, there may be areas we need the acceleration, but we don't. But notice we have the velocity, which is the equivalent of f prime, and a point on the position function, which is the original. So we have what we talked about before. They say that the particle changes direction exactly once. Find the position of the particle at that time. Okay, we'll just very quickly find the position or where it changes direction. So I've plugged, nope, that's not it. I need to plug the velocity function in here. So that'll be 2 sine of e to the t over 4 plus 1. And I'm going to make sure I'm in radian mode. Okay, good deal. So let's look at the graph. We're only looking at this from 0 to 6. But we know a particle changes direction whenever the velocity changes signs. So we're looking for the spot where the velocity changes what it looks like will be from positive to negative. Now, if you don't remember all this position velocity stuff, for the moment, that really is okay. What I want you to focus on is more so how we find that other position. This will be the only example where we have to talk about particle changing direction. But it changes direction, it looks like pretty close to 5. If you count over 1, 2, 3, 4, it looks like it's pretty close to 5. So what I'm going to do is go to Second, Calc, and I'm looking for the 0. And then it will ask me for the left bound, so I'll move just to the left of that spot. And tell you what, the calculator is moving very slowly for me when I try to do that. So I know it's hitting the 0 somewhere between 4 and 6. So I'm just going to tell it the left bound is 4 and hit enter. And the right bound is 6 and hit enter. And when it says guess, I'll just ignore it and hit enter again. Okay, so the point where this happens is 5.195. So it changes directions at 5.195. So that's where the particle changes direction. But I want to keep that number exactly, so I'm going to hit quit right now. And if I type x, it actually has that number saved in there for me. But if I do other stuff, it may change what's solved for x. So I'm going to store, this is the button right above on. I'm going to store that number into a. So just hit alpha, a. You can pick a different letter if you want, doesn't matter. And now, anytime I want that exact number, not just the rounded off version, but the exact number, I can just type in A. Okay, so let's go back. That's worth reviewing, but the main part I want you to focus on is what's happening now. For 0 to 6, the particle changes direction exactly once. Okay, we found out that that happens at 5.195. Find the position of the particle at that time. So we have the velocity equation, that's the derivative. We know one point on the original. We know at 0 the position is 2. So we want to find the position at 5.195. So we're looking for x of 5.195. So if you think about it, the integral from 0 to 5.195 of the velocity equation would equal the position function at 5.195 minus the position function at 0. That's just the first fundamental theorem. We take the antiderivative. The antiderivative of the velocity function is the position function. And then we plug in the top number, 5.195, minus the bottom number, 0. So if I want to solve for this, I just need to add the x of 0 to both sides. So x of 0 plus or minus the integral from 0 to 5.195 of v of t dt. That will tell me the position at the time 5.195. x of 0, they told us, is equal to 2. So I'll just put 2 in there. And this integral I can do in my calculator. So I'll go over to my calculator, hit Math 9, go from 0 to a, because I saved the exact number, 5.1955 and so on, into a. And I already have the velocity equation plugged in. You can retype the equation, or you can go to variables or vars, then go over to y variables. So variables, y variables, function, y1. So that just plugs it in for me so I don't have to retype the whole thing. X. So this is finding the integral from 0 to 5.195 under the velocity equation. And it turns out to be 12.134. So 2 plus 12.134. So the position at the time it changes direction is 14.134. Again, as far as the changing direction, as far as this unit, it's okay if you don't remember that stuff, but understanding how I got all this does matter a lot right now. So let me show you one more. I'm purposely doing 2 of the harder ones I found, and the 2 you have are easier for homework tonight. So where t is greater than or equal to 0, a particle moves along the x-axis. The velocity of the particle is given by this equation, and the particle is at position x equals 2 at time 4. So there's a couple tricky things about this one. First of all, they give the ordered pair to you in what feels like a backwards way, because this is the position function, which means it's actually the y value, and this is the time. So our ordered pair is actually 4, 2. Or you could say, if you plug 4 into the position function, the position is 2. Then it says find the position of the particle at time 0. So we're trying to find x of 0. So if you think about it, using the fundamental theorem, we know the integral from 0 to 4 of the velocity equation is equal to the position of 4 minus the position at 0. Again, antiderivative of the velocity function is the position function. Then you plug in the top number minus plug in the bottom number. So we already know x of 4 is 2. And we can solve for the integral in our calculator. So we'll do math. Just one second, let me clear out here. Math 9. We're going from 0 to 4. I'll plug in the velocity equation. 1 plus 2 sine of x squared over 2. And put in dx. Actually, I do need to close the parenthesis there. There we go. Closing the sine parenthesis because the other one is for the whole integral. And I put dx. 1 plus 2 sine of x squared over 2 dx. I plug this in. I get 5.815. 5.815. And I subtract 2 from both sides. That's equal to negative x of 0. So I just need to multiply both sides by negative 1 and find that the position at time 0 is negative 3.185. That's it. Now I want to show you one reason I actually tend to teach this using the fundamental theorem of calculus formula instead of just jumping straight to what I had you write down here. Now both are true and both work, but here's where this one was a little bit trickier than others. If I had gone ahead and done what we normally do and solved for x of 4, let me show you what would have happened. If I had added x of 0 to both sides, You just have to be careful and note that it wasn't this one we were looking for this time. It was actually this one. They gave us x of 4. So what was different was we knew x of 4 was equal to 2. We found this equation, or the value of this integral in the calculator. It was actually x of 0 that we'd have to solve for. Now that still works completely. You just have to be careful in paying attention to which point they gave you and which one you're looking for. And we get the exact same answer this way. We subtract 5.185. We get x of 0 equals negative 3.185. Okay, I just have you practicing 2 examples of this, and these 2 are pretty straightforward, I assure you. If you just use the fundamental theorem like I have set up on both of these examples, you'll be able to do these just fine. But the important thing is to learn how we can use the fundamental theorem to solve for a point on the original given a different point on the original and the derivative.